Welcome to this video on matrices, covering their introduction, different types, operations, and various applications in mathematics and engineering. A matrix is a rectangular arrangement of numbers, symbols, or expressions, organized in rows and columns, and represented using square brackets. The example shows matrix A with m rows and n columns. One example of a matrix application is in representing systems of linear equations, which is commonly used in mathematics and engineering. The system is converted into a matrix representation for easier solving. Matrices are also vital in representing vector systems in physics and engineering mechanics. Individual vectors can be represented, and multiple vectors can be combined into a single matrix. In strength of materials, matrices are used to represent the state of mechanical stress at a point, which is often visualized as a three-dimensional stress block. They help in the analysis of stresses, strains, and forces acting within a material. Matrices are especially useful in determining principal stresses, maximum in-plane stress, and their directions using eigenvalues and eigenvectors. They also play a crucial role in bending, torsion, and deformation analysis of structural elements. Electrical circuit systems governed by Kirchhoff's laws utilize matrices in electrical engineering to represent and solve the system of equations that describe the circuit. Matrices are fundamental in computer graphics and AI systems, particularly in machine learning and image processing, where an image is represented as a matrix of pixel values. Matrices offer several important advantages in mathematics and engineering. They help simplify complex calculations by organizing large amounts of data in a clear and systematic form. Matrices provide an efficient and compact way to represent information, making analysis and computation easier. Using matrices, multiple equations can be solved simultaneously, with less effort and fewer errors. They are widely used in many real-life applications, such as engineering analysis, physics, computer graphics, data processing, and economics. Because of their versatility and efficiency, matrices play a vital role in both theoretical studies and practical problem solving. The order of a matrix is defined by the number of rows m, multiplied by the number of columns n, written as m by n. For instance, a matrix with 2 rows and 3 columns has an order of 2 by 3. We will now discuss various types of matrices. A row matrix is a matrix that contains only a single row, regardless of the number of columns. Conversely, a column matrix is defined as a matrix that has only one column, regardless of the number of rows. A square matrix is characterized by having an equal number of rows and columns, meaning m equals n. Square matrices are widely used in engineering and mathematics because many important operations are defined only for them. The determinant of a matrix exists only for square matrices. Eigenvalues and eigenvectors are also defined only for square matrices. The zero or null matrix is a matrix where all of its elements are equal to 0. A diagonal matrix is a special type of square matrix. In a diagonal matrix, all the elements outside the main diagonal are 0. Only the elements along the main diagonal may have non-zero values. The unit or identity matrix, represented by I, is a special type of diagonal matrix, where all diagonal elements are 1 and non-diagonal elements are 0. A scalar matrix is a square matrix where all diagonal elements are equal and all non-diagonal elements are 0. An upper triangular matrix is a square matrix in which every element below the main diagonal is 0. A lower triangular matrix is a square matrix in which all elements above the main diagonal are 0. Moving to matrix operations, the first is addition of matrices, which is only possible if the matrices have the same order. To add 2 matrices, we simply add their corresponding elements. The result is a new matrix of the same order. Scalar multiplication involves multiplying every element of a matrix by a single constant number, known as a scalar. Matrix multiplication requires the number of columns in the first matrix to equal the number of rows in the second matrix. If this condition is not satisfied, matrix multiplication is not possible. In multiplication, each element of the new matrix is obtained by multiplying the elements of a row from the first matrix with the corresponding elements of a column from the second matrix, and then adding the results. The resulting matrix's order is the rows of the first by the columns of the second. The transpose of a matrix, denoted as A power t, is found by interchanging the rows and columns of the original matrix. A symmetric matrix is a square matrix that remains unchanged when transposed, meaning it is equal to its own transpose. These matrices are often found in physical systems like stress and inertia analysis. These matrices are always diagonalizable, but not necessarily invertible. The determinant of a matrix is a scalar value calculated for a square matrix, indicating properties such as invertibility. For a 2x2 matrix, it is calculated as shown. Calculating the determinant for a 3x3 matrix involves a more complex expansion method, as detailed in the example. A singular matrix is a square matrix whose determinant is exactly 0. For a singular matrix, the inverse does not exist, and its rows or columns are linearly dependent. A non-singular matrix is a square matrix with a non-zero determinant. This type of matrix is invertible, and its rows and columns are linearly independent. The inverse of a matrix, also called the reciprocal, can be calculated using the adjoint or adjugate method for a non-singular square matrix. First, calculate the determinant of the given matrix. If the determinant is non-zero, the inverse exists. Next, find the cofactor of each element to form the cofactor matrix. Each cofactor is calculated by eliminating the row and column of the element and finding the determinant of the remaining 2x2 matrix. Then, take the transpose of the cofactor matrix to get the adjoint, also called the adjugate, of the matrix. Finally, multiply the adjoint by 1 divided by the determinant to get the inverse of the matrix. The conjugate of a matrix, often used when dealing with complex numbers, is obtained by replacing each element with its complex conjugate. The video will now cover important matrix properties, starting with the properties related to matrix addition and scalar multiplication. Next are the key properties governing matrix multiplication, such as associativity and how it interacts with the identity matrix. This slide outlines the properties associated with the transpose operation, including how it behaves with addition and multiplication. Here we see the crucial properties of the determinant, which apply only to square matrices, such as how it changes under transpose or multiplication. This slide details the fundamental properties of the inverse matrix, including the double inverse and the inverse of a product. The final type of matrix we consider is the orthogonal matrix. For an orthogonal matrix, the transpose of the matrix is equal to its inverse. This means that when the matrix is multiplied by its transpose, the result is the identity matrix. In an orthonormal matrix, the rows and columns are not only perpendicular to each other, but also have unit length. These matrices are important because they preserve lengths and angles during transformations. Thank you for watching.